Lecture 2, vector calculus. So why we need to learn vector calculus? Well, it's pretty simple because if you look at Maxwell's equations are these four equations. So these are the differential forms, and this is integral form. And then by the end of this class, by the end of this semester, you should be able to understand what these equations mean, right? So it's necessary that you know what these divergence and curls mean, and also these integral symbols mean, right? That's kind of necessary thing. So in this lecture notes, I will teach you about these things. Oh, okay, probably not only this lecture note, but the next one also. So you will learn about what's scalar and vector, which is easy. And then we will also learn a basic topic of vector algebra, of vector addition, vector subtraction, multiplication, which is also easy. And from here, some of you are kind of new, like vector differential operations, like gradient, divergence, curl, and Laplacian. And I'm going to tell you not only the definition, mathematical definition of these, but also give you some geometrical sense of what these means, and also how this is used in physics, so that you can get some sense what these vector operators mean. And then we will learn about like multidimensional integrals, like line surface volume integrals, and then some important theorems like divergence theorem and Stokes theorem. And then finally, in the next lecture notes, we will learn about different coordinate systems and how to transform between those. So how many of you are familiar with everything here? Everything appeared here. Please raise your hand. If you're familiar with all these topics, please raise your hand. Okay, 1, 2, not many. Okay, good, good. So at least this is meaningful, right? To cover this. And just to check, how many of you doesn't know about differentiation and integral, like not like a multidimensional differentiation, but just a simple differentiation? How many of you doesn't know how to do 미적분? Okay. Okay, at least everyone knows simple differentiation and integration. Okay, so that's good. That's good. So I assume that is the only thing that we need to know before we jump into the topic. Okay, so I'll go fast for these elementary subjects. So the scalar and vectors. I mean, everyone knows about the scalar and vector, right? So scalar is a quantity that only has magnitude, like energy, work, power, temperature, just defined as a single number, right? This is just a magnitude. Temperature is just a single number. It doesn't have any direction, right? And vector, instead, both have magnitude and direction, which means it has multiple numbers. You need many numbers in order to determine vector. If it's a three-dimensional vector, you need 3 numbers to define it. So the examples are velocity, acceleration, momentum, force. All these things has direction, not only the amplitude, but also the direction, right? And then the fields, we will talk a lot of field, and field has different definitions in like mathematics. But in physics, we define field as just a physical quantity that has a value for each point in space and time. Okay, so what does that mean? Take an example. This is a temperature field, right? Because you see this is a map of the Earth, and then at each point in space, temperature is defined, right? So in that sense, this is a temperature map. right? And here too, if you have a, say, Earth here, and then you want to know the gravitational force around it, gravitational force has a direction and also the magnitude at each point in space. So in that sense, this is a gravitational force field, right? So the left ones are scalar fields, right? Temperature field, charge density profile, electric potential profile. These are what we call like a scalar field. And then these gravitational force, wind flow distribution, and electric field, magnetic field, which we are interested in, are the examples of vector field, right? So how to describe vectors? So we use, typically what we use is we use standard basis, right? AX, AY, AZ. By the way, we're gonna use small bold A for unit vectors, okay? From now on, small vector A is just dedicated for unit vectors. So AX means the vector along X direction having length 1, right? And then AY is length 1 vector, unit vector with direction Y, okay? So you can understand that. And then vector A, given like every vector A in 3D space, can be represented as a linear combination or the sum of, you know, AX, AY, AZ vector and their coefficients, right? And these coefficients we call like AX, capital AX, capital AY, capital AZ are called components, right? So these AX, AY, AZ, the small things are bases, and capital AX, AY, AZ are the components, right? So you know the distinction. Okay, and the vector addition and vector mod. Oh, by the way, if you have any question during the class, you can just type in your question in the chat box so that I can address your question in real time. Okay, and this is highly encouraged, and this is also important for you because, again, this is really important topic. So you have to understand this clearly in order to move on to the real electromagnetism topic. So if you don't understand anything, just type in the chat box. So vector addition and subtraction. I mean, this is also an easy topic, so I should go fast. So everyone knows this parallelogram technique, right? So when you want to add two vectors, A and B, then you know, if you write how to add them, it's like you just add their components, right? Component by component. And then graphically, it can be represented like this. You have an A vector and B vector, then you create a parallelogram based on these vectors, right? Parallelogram based on these vectors. And then the diagonal is the addition of two, right? And the subtraction is actually similar. It's just A minus B is nothing but A plus minus B, right? So all you need to do is to flip B vector so that you make minus B vector, and then adding that to A, then you get D, right? So basically it's the same. And then again, component-wise, you can just add, subtract them. AX minus BX, AY minus BY, AC minus BZ. Okay. So basic algebra of addition and subtraction. These are the properties, like a commutative means A plus B is equal to B plus A, which sounds trivial, but it's not trivial for some operations. But here it's the case. So A plus B is equal to B plus A. Okay, that's commutative. And then associative means it doesn't matter which operation you do first. So let's say you have A plus B plus C. It doesn't matter whether you do B plus C first or A plus B first, it wouldn't affect the result. So that's associative properties. And then distributive property is that, like, if you multiply K here, then K is just going in both elements. And then if you think about the multiplication between a vector and a scalar, it's also a commutative and associative. Okay. So any questions so far? I thought this part is very basic, so I didn't spend much time on it. But there, it is possible that some people is not familiar with this. So let me know if you have any question. Okay, so I'll assume this is easy enough. And then we have 4 exercise problems, which I think is a bit too easy. So I'll just give you the answer, okay? So it's, I don't want to spend time too much on it. So the position vectors Q and R, RQ and RR is given like this, right? Just 2AX, 4AY, 6AC, and then 3AY, 8AC. So one distinction between these two is that Q, the large Q here, is about the point, right? It's the point in space. And then the position vector means the vector connecting the origin and the point, right? So the point itself only have coordinate numbers, right? But as you make it into a vector, so position vector, your position vector is just OQ or OR, right? And then RQ plus RR is just, again, adding component by component, right? 2 plus 3, I'm sorry, 2 plus 0, and 4 plus 3, and 6 plus 8, right? And then the displacement vector QR. So let's say displacement vector. So you have so here you have origin O, and then you have Q, and then you have R, right? So RQ is this, and RR is this, and then the displacement vector QR is from Q to R, like this, right? So the question is, how can you write it? Again, this is nothing but RR minus RQ. So if you do that, you can easily obtain the coordinate numbers. And then the distance between Q and R, that is the magnitude of QR vector, which is square root of the square of each component. So some of these haven't properly covered in the previous slides, but anyway, I thought that this is kind of elementary things. So I just brought this up without the background. But just let me know if any of this is not familiar with you. Okay, so I'll assume that this is easy. Everyone is following. Okay, so now we'll move to still fundamental, still elementary, but not that easy things. So now we move on to the vector multiplication. Okay, there are 2 ways to multiply 2 vectors. One is scalar product, and the second is vector product. Scalar product is written like this, like A dot B. So because it's written like that, we call, sometimes we call this as a dot product, okay? Or inner product, same thing. And then magnitude of this is AB cosine theta. And then here, again, here's the notation. A, bold character means vector, in my lecture notes. And then here, like italicized unbold characters means scalar number. Okay. And then here A and B are defined as the magnitude of A and magnitude of B. So A dot B is equal to AB cosine theta, right? And then this can be also calculated by multiplying the components by components and add them up. Okay, so this is a scalar product. What's the meaning of scalar product? What geometrical meaning of scalar product is the projection. So for instance, if somebody asks you to calculate the component of A along the direction of B, okay, then you can immediately decompose A into two vectors. One is this, one parallel with B vector, and the other like this, right? Perpendicular to the B vector. And then if you add these up, you get A. So component of A along direction B is A cosine theta, right? And then you can obtain this by performing this operation, A dot AB. Again, small a means unit vector, and the subscript B means it's along B direction. So AB, of course, is equal to B divided by B, right? So vector B divided by its magnitude. So that magnitude becomes 1, but direction is the same as B. So if you do that, it becomes A cosine theta, right? So again, the projection, the dot product means projection. Okay, projection of A vector along B vectors. So if you look at the algebra, the scalar product satisfies commutative relation. B dot A is equal to A dot B. And it's also distributive. So A dot B plus C is A dot B plus B dot C, right? So sorry. A dot B plus A dot C. Sorry, I have a typo here. Anyway, it's distributive. I have to change this. Okay. And then how it's used in physics? It's used in physics like when you evaluate the force and displacement, like evaluate work from force and displacement. You probably learned this in elementary physics class, right? When the force, so let's say if you apply the force without any motion, or if you apply the force, but the motion is perpendicular to the direction of the force, then you are actually not doing any work, physically speaking, right? So F dot S means you only count the force when force and the displacement are in the same direction, or at least in similar direction. And then this exercise also is kind of easy. So you can use this scalar product thing to prove second law of cosine. So think about this triangle. You have A and B and C. And C is defined as A minus B here, right? And so C dot C is equal to A minus B dot A minus B, right? And then if you expand this, A dot A, B dot B, and then these inner products, A dot B, B dot A, right? So this is equal to A squared plus B squared minus 2A dot B. And then A dot B is again 2AB cosine theta, right? So if you summarize this, C, the length of this side is equal to square root of A squared plus B squared minus 2AB cosine theta. This is the second law of cosines. Okay. And then another type of multiplication is vector product. Vector product, sometimes called cross product because we have a cross here, right? We use cross sign to describe this, or sometimes it's called outer product, okay? And the vector product of two vectors is also a vector, another vector. And then the direction of that vector is normal to both A and B. So you can use a right-hand rule, like if you have your palm passing through, like sweeping through A and B, then the direction of your thumb becomes the AN vector, like this. So if you're sweeping through this, this is your vector direction. And the magnitude is the area of the parallelogram having A and B as sides. So this area is your magnitude, right? Or in other words, AB sine theta. And this one can be also calculated by using this determinant equation. AX, AY, AZ, and X. These are the determinant equation. How many of, so like everyone knows determinants, right? Does anyone, is there anyone who hasn't heard of a determinant? Determinant equation, everyone knows it, how to evaluate, right? Okay. Okay, good. And right, and then basic algebra is a bit different here. First of all, A cross B is not B cross A. You have minus sign here, right? This is anti-commutative relation, right? Right, because you have a minus sign. And then why? Well, because it's direction. And as I said, A cross B, you apply the right-hand rule. So direction becomes upward direction. But if you do B cross A, of course, it's opposite. It's the opposite. So the magnitude is the same, but the direction becomes opposite. So it's anti-commutative. And then it's not associative. So if you have A cross B cross C, it actually matters which evaluation you do first. So if you do B cross C first, then the value, the result is completely different from A cross B first. Okay, so this is not associative at all, but still distributive. Okay, I made here also a typo. But anyway, it's that. And then how to use in physics, especially in electrodynamics, it's used to describe Lorentz force. So if there is a charged object in the magnetic field, and this charged object moves with velocity v, then the force exerted on this charged object is F equals QB cross B. Okay, so the cross product is conveniently used in this case. So the force that this charge feels is not parallel to B field nor parallel to the velocity, but it's perpendicular to both, right? Okay, so it was a bit, okay, so before I finish, before I move on, there's another one. There's a triple product. It's not just, it's not actually a thing, but like there's an interesting relation, like A dot B cross C is equal to B dot C cross A and C dot A cross B. Okay. So, and then this property can be easily proved by just looking at this geometrical interpretation. So let's look at the first equation, B cross C dot A. So let's say this is A, B, C. Then B cross C is again the area of the bottom plate. And the and the direction is perpendicular to the bottom plate, right? And now you take a dot product with A, which means you are doing actually the projection of A to this direction. So you have height of this object. So height multiplied by the area gives you the volume of the parallelogram. I mean, this is parallelepiped, right? And the similar thing applies, can be applied to all these equations. Like if you look at the second one, C cross A gives you the area of this surface. And then if you take the dot product with B, and you get the volume. Same thing here. So it's just the different ways of describing the volume of same parallelepiped, right? So in that sense, this equation makes sense. I mean, these are all same. And then this, I don't want to give you a proof because I don't have any sort of intuitive proof here. But this is easy, good to remember because it's kind of famous thing. A cross B cross C is equal to B multiplied by A dot C. So A dot C is scalar, right? And then C multiplied by A dot B. This is also scalar. Okay, so this is just a subtraction of two vectors. And this is called back cap rule because BAC, right? The reason this is called back cap rule is just to help you memorize easier. But this is actually, people actually call this as a back cap rule. And this expression is useful in many times. So probably it's better to memorize. Okay, so now let's see how good your understanding is about these, what we learned. So please prepare some pens and papers and do this exercise. I'll give you 3 minutes, and then after 3 minutes, you can just type in the question in the chat, the answer in the chat box. Okay, time is up. So how many of you got the answer? Can you raise your hand? How many of you, if you got the answer, please raise your hand. Okay, majority. Most of you, okay, majority of you got the answer. And can somebody type in the answer for ABC in the chat box? Most of you got the solution, but you're hesitant to type in your solution to the chat box. Okay, good. Okay, good. Good. Right. Okay. So yeah, so it seems like Lee Chung-pil got the correct answer, and many of other people also got the correct answer. Right. Thank you. So let's like begin one by one. Like let's do one by one. And I don't want to go to the detailed solution, but the scalar product of P along Q is like P dot AQ, right? P along direction of Q. And then AQ is P dot Q divided by the magnitude of Q, right? And this is 2/3. And the second one, the area of triangle having P and Q as sides. So P cross Q gives you the area of parallelogram, right? Area of parallelogram. So in order to get the triangle area, you need to divide by 2, right? So that is square root of 41 divided by 2. And the third one, the unit vector perpendicular to both P and Q. So like P cross Q, the direction of P cross Q gives you the direction, like the perpendicular to P and Q, right? So in order to get a unit vector, you need to divide it by magnitude of it. And because you have 2 choices, right? You have up and down choice, so you can put plus and minus, right? So these are the answers for this question. So before we move on, do we have any question? I just want it. So if you have any question, please leave here. And if you don't have, I think we are ready to move on to the actual vector calculus, like vector differential operators. Okay, so I'll assume that there's no problem. By the way, if you have any question, like it's recommended to put in, type in the chat box. But if you're your question is a bit too long, or in any region, if you want to ask privately, I'll hold the office hour right after the class. So if you have any question, private question, like regarding the course contents or anything, like about your future or whatever, so you can just stay, okay, and then ask the question. Right. And there's one question actually coming in. 이상후, B, why is it negative? Can you elaborate this question a little further? I just don't understand what exactly you're talking about. Because this is just a cross product of P and Q. Oh, here, yeah, but but I don't think so. Like if you just evaluate this, for instance, just the AX component, you know, this AX component, this is like AX 0, -1, -1, 2, right? So AD minus BC gives you -1, right? So the first term is -AX, right? I'm not sure whether you ask this, but anyway, this is why you have negative sign. If that's unclear, you can, you know, still ask further questions in the office hours. Okay, so now let's move to the real topic. From now on, I guess many of you are not familiar. Okay, even though you learn this, probably you are not familiar with this. So just you know, pay attention, and then if you miss this, you will have difficulties in understanding the following things. So just pay good attention to this. So ordinary derivatives. This is if you have a function f of x, then you can always define df dx, right? This is ordinary. I mean, not always. Of course, f should satisfy certain conditions, but assuming f satisfies all these conditions, you can define ordinary derivative, df dx, right? And then the meaning of df dx is slope of this curve, right? You are familiar with this concept, right? So derivative is about slope, right? Especially in this 1D case. So the question is, what if we go to multidimensional scalar function? Like, okay, so before then, I have to say this. So if you have a multidimensional space, then we can apply, we can define the del operator. Del operator is a vector differential operator defined like this: partial x, ax, plus partial d, ay, plus partial z, dz. Okay, so partial derivative along x, and in x direction, y direction, z direction. And this del operator, the partial derivative operator, can be applied to scalar field or vector field. So if it's applied to scalar field like this, or it can also apply to vector field like this without any symbol here, we call it as a gradient, okay? And then if this vector operator is applied to another vector field with dot product, we call it as a divergence. And then if it uses curl operator, cross product, we call this as a curl. Okay, so depending on how this operator acts on the field, these have different names: gradient, divergence, and curl. Okay, and then of course these names have meaning, right? Like gradient, divergence, and curl is not just random name; it has meaning. And then from now on, what we are going to learn is why this is called this name, and what's the geometrical interpretation of these things, and also how this is used in physics. Okay, so that's how what we are going to learn. So first, we are going to do gradient. So before then, let's go back to our slope problem. Okay, so now let's assume that we have a multidimensional space, right? So f, the function f, is defined on xy coordinate, for instance, right? And then if you draw like f as a function of xy as a height, then you have this map, right? It's going up and down type of a map. And then here's an interesting question you can raise. If somebody asks you here, what's the slope here? What's the slope of this mountain at this point, or slope of this function at this point? It's kind of difficult question, or I would say ill-defined question, because slope can only be determined when you assign direction first, right? For instance, like in this case, if you assign the direction like this, then the slope is 0, right? Because if you go to this direction, you don't go higher or lower. It's just a, straight left, right. But if somebody asks you the slope along this direction, it's very steep, right? It should have a really high value. So in other words, in order to define a slope in multidimensional function, you need to either define the direction first, or your slope must be also multidimensional, right? Like you can tell like this. Oh, if somebody asks you what's the slope? Oh, okay. If you go this direction, the slope is 0. If you go that direction, slope is 1. That can be an answer, right? And if you're in the middle, you can just do some algebra in order to get the slope value, right? So gradient operator gives you this quantity, like the value related to the slope in a multidimensional manner. So let's look at this. So now let's look at the gradient operator again. You have function differential and partial differential operator, partial derivative along x direction, and partial derivative along y direction, and partial derivative along z direction, and each have direction, the unit basis vectors, right? So this basically tells you that if you go along x direction, this is your slope. If you go along y direction, this is your slope. And if you go along z direction, this is your slope, right? So in that sense, gradient defines slope in multidimensional thing, right? And of course, the magnitude of a gradient vector tells you the maximum slope that you can achieve, right? So why this is the case? So let's think about this. So if somebody asks you, what's the direction if you go along x direction? I mean, what's the slope if you go along x direction? Then what you need to do is this dot ax, right? This is a projection operation. So you have a gradient, and then if you project the gradient along x direction, you ended up having this, right? So exactly this is how you define the slope along x direction, right? So let's say if you have arbitrary unit vector, then the magnitude of this is defined as this cosine theta, right? So theta is the angle between this and that. So if cosine theta is 0, then it's maximized, and the maximum value is this gradient of v, right? So gradient of v, the magnitude of gradient of v is the maximum slope you can get, right? And then in order to get the direction, of course, that direction must be, this only occurs when theta is 0, right? So the direction of gradient of v tells you the direction of maximum increase, right? And then this becomes evident if you look at this examples. So now assume that this, white means low, black means high. Okay, then this. Okay, Kang Yung asks if can we add vector sign on del operator? Well, it really it's just a preference. But you shouldn't write this, even though I write that just a minute ago. This is not a proper way to write things. You can either write, I'm sorry, you can either write this. I mean, this is the proper way of writing things. Sorry, if this misleads you, and this is not the way of writing proper manner. Okay, thanks for the clarification. Okay, so going back to this thing. So if this is low and this is high, that means you're actually watching at a mountain from the top, right? And then if you evaluate the gradient of V, you have this vector field, okay? Which means, your vector field, your gradient always pointing the top of the mountain where the slope becomes maximum, right? And the actual magnitude tells you about the maximum slope. And similar applies here. So if the white is low and black is high, that means you're looking at something like this, right? So if you evaluate the gradient, it's just going this direction, like just toward this, right? Which means if you go along that direction, perpendicular to the gradient, you experience zero slope. There's no slope at all, right? And if you're going along gradient, then you experience maximum slope, right? So you see what this gradient mean then, right? Its magnitude is maximum slope. Direction is the direction of maximum increase. Okay, so where to use it? It is used in physics, to connect force field and scalar potential field. So this is an example. Like we will encounter another example in electrostatics, but this is just an example in gravitational force. So you have force field and you have a gravitational potential. In order to connect two, you use a gradient. Okay, so this is how your potential looks like. If you have an Earth here, then your potential, scalar potential, looks like this. Okay, minimum at the on the Earth's crust, and becomes higher and higher as you go move away from the Earth. Okay, and the force it feels is toward this direction, right? Any massive object feels the attractive force due to the Earth, right? And the direction is this, right? The gradient of the potential. The reason we have negative sign is because force is always going downward, not to upward, right? So water always flows downhill rather than uphill. So in order to account that, we have negative sign here, right? It's going down. Gradient is defined along increasing direction. So you have negative sign, now you have this decreasing arrow. Okay, so this is a basic explanation of what gradient is. So let's say for next 3 minutes, please do this exercise. Okay, so you can begin now. Okay, time is up. And how many of you got the answer? If you got the answer, please raise your hand. Okay. How many of you? Okay. Okay. So about half, slightly more than half, actually. Okay. So which means I think it's getting more and more difficult. Although this is already the beginning of the stuff. So can you type in the answer for B and C? I mean, A is too complicated to type in, but B and C is just a single number. So can you type in the answer of B and C, solve problem B and C in the chat box? Oh, everyone get the correct answer, which is pretty surprising. Okay. Okay, yeah, that's right. 2 square root 2 and negative 2. So it's, you know, the way I approach this type of a problem is to see, so in order to prevent any mistake, what I usually do is try to look at this function first. Okay, before, of course, you can begin with like directly start with this, right? And there's no problem doing this. Just calculate this first, and then start working on this. There's no problem doing this. But if I were you, I approach this problem like, okay, so V is x squared minus 2x plus y squared. So you can always make it into x minus 1 squared plus y squared plus 1, right? And then you can immediately notice that in xy plane, this is the minimum point, right? Because x equals 1 and y equals 0 is the minimum point. So from then on, it'll be like this, right? It's a second order increase, right? So if you have this picture in mind, it's highly, it's less likely for you to make any mistake in solving problem. Okay, so like for instance, if you have, now you know this, and then this is your bottom, right? So you can imagine your gradient should look like this, right? It should be like this. And then the magnitude should increase as you move away further because it's x squared. So if you take the derivative, it should increase as you move further away, right? And then now you are interested in 0.212. So 2, 1 is here, right? And then 2 is along, of course, there's a z direction too. So it's like this. So, you know, having this in mind, and then directional derivative at P toward the origin. So you have this direction. Oh, -1. Yes, -1. That's right. Jung Yeonho is correct. Yes. I supposed to say -1. Yes. Anyway, so that's that. Like once you get the problem, what I suggest is first look at the function carefully, and then there's any way that you can guess how it looks like. Okay. And then with that information, you hardly miss the correct answer. Okay, so that's what I wanted to say. And then, of course, in order to actually evaluate the number, you need to go through these steps. And surprisingly, every one of you got the correct answer. So it's pretty amazing to me. And so this is about the gradient. Again, the gradient is about the slope, but we have multivariable. So slope is not defined in a single number. So we need multiple numbers, and the gradient is how you define it. And next time, what we are going to learn is divergence and curl. So as I said, divergence and curl is you apply, I'm sorry, like your gradient, I'm sorry, your del operator with a dot product, this is called divergence. And then if you use a cross product, this is called curl. And then the motivation for that can be simply drawn like this. So you can definitely see that there is something special in these vector fields. Let's say these are your vector fields. Okay, so these are your vector fields. And then you can say that you would say that this vector field is normal, right? Nothing special, it's just going flow from left to right, right? But this one is strange, right? But this one, you have a special point here. And then from here, things are kind of, diverging, right? And then this one is also special in a sense that it looks like it's kind of, rotating around, right? So how much a vector field is being generated, and how much this vector field is rotating can be described by divergence and curl. And you will see why this is the case in the next lectures. Okay, so probably in your when you learn this divergence and curl first time, you probably learn about how to evaluate this, right? So like partial x, bx, partial x, by, partial c, bz. This is the definition of divergence, and definition of curl is that. But that's not the point. I mean, that is of course important, but the more important thing to understand what is the meaning, what is the geometrical interpretation of that. And that's really important in understanding or applying this concept in physical problems. Okay, good. So I'll finish here.